So the final talk this morning is by Yvonne Geyer from the Institute for Advanced Study.
So thank you so much. I want to add to all the other speakers already and say that it's been really an amazing conference at a wonderful location. So thank you to all the organizers. So what I want to tell you about is, in line with what JJ told you about this morning, some progress in the calculation of scattering amplitudes in field theories. And I want to focus specifically, in this case, on massless field theories. And what I'm going to try to convince you is that the beauty and the simplicity of the models that we've seen and that JJ described to you this morning, in particular the CHY formulas and the scattering equations, can be understood best from some worldsheet models that are strongly similar to string theories. And in fact, so much so that you can really take it as a red line through all my talk, that anything that you can do in string theory will work with some slight modifications in these models. And the aim is to show you that, well, the CHY formulas are beautiful, but they really only give us something at tree level. They're just formulas. So if you want to push that beyond tree level and really find out something about loops, you have to better understand the theories that actually underlie them. Okay. Better? Okay. Can you still hear me? Okay. So let me just briefly tell you, to avoid confusion, what it actually is that I want to tell you about and what it isn't. So in particular, the worldsheet theory that we all know and love best is string theory, and quantum field theory, as you all know, comes out of that in the alpha prime going to zero limit. So what I want to tell you about is actually remarkably different from that, in that what we want to focus on is a strict equality here. Now, JJ pointed out to you this morning already that there's been quite a long history of these models going back to 2003, and I've listed some references here. But what they all have in common is, first of all, they're quite restrictive. They usually work in 4 dimensions and for maximal supersymmetry. Just as a side note, there's an interesting point that they actually map to an auxiliary target space, not directly a string theory to space-time. And that's going to be something that we actually see again. But the second problem that we had with them is that they're actually not, there's no good way that we know of to extract loop corrections from them. So what I want to talk about are the models that started off with the CHY formulas and then were formulated under the name of Ambitwistor Strings by Mason and Skinner. And these, what I will tell you about is that these actually have fully well-defined corrections to higher loop orders and have a strict equality here. They really describe quantum field theory on the nose. And how they achieve this is by the fact that they localize the integration over the moduli space that we know from worldsheet models on something that is called the scattering equations that you've already heard a few times today. Okay, so let me just, in one slide, if you have one take-home message today, so what are Ambitwistor strings? They're just 2-dimensional chiral CFTs with an auxiliary target space. And this target space is really the reason that they give us these huge simplifications, because they map into the phase space of null geodesics. And if someone told you sort of what is the most natural space that you can write down massless amplitudes or describe a massless theory, field theory in, well, this should be your first natural guess for that. Okay, so let me start from the beginning and tell you a bit about what these formulas actually are that inspired all this progress. So this was developed by Cachasso, He, and Yuan, and they describe general tree-level amplitudes in massless field theories as an integral over the moduli space here. But what you can nicely see is that this integral here is completely localized on these equations, which are called the scattering equations. Now, my sigma I are just marked points on the Riemann sphere in this case. And this integrand that I've denoted here by IN is something that just depends on the polarization, if if the theory that you're describing has that, or and in any case, the momenta and the marked points. So just to give you some short examples, for gravity, this would be some Pfaffian of some matrix, where the matrix, again, just depends on your kinematic data. And what you can see nicely is that these encode beautifully the double copy or the color kinematics that you heard about in the first session this morning. So what you do to go from gravity to Young-Mills is that you just substitute one of these factors that have, that is really your kinematics by a color factor, something that is just a Park-Taylor factor with the appropriate trace structure. And just to complete the family, I've included the bi-adjoint scalar here, where you replace the second copy as well. And in fact, there's a much bigger theory of, or basically any massless theory can be described in this way. The more symmetry you have, the nicer these forms here will be and the more compact. You might have noticed that I've said it the other way around from what you usually heard this morning. So I've started with gravity and said substitute a copy of gravity by the color structure. So that is another sort of something that you will notice throughout the talk, that the model that is best defined and is really anomaly-free is type 2 supergravity. So that hence why I've structured it this way around. The other thing that I want to mention is that, well, usually you would discuss this in the way that you, or work with this, you could solve these scattering equations and sum over the solutions with the Jacobian. There's actually been a lot of progress on solving, or well, on evaluating this without actually ever solving these. And I won't have time to do this justice, but that's been some very remarkable progress. Now, let me just spend a moment on these scattering equations that you've seen here, because they're very fundamental for the whole structure of these amplitudes. So the most convenient way, despite the fact that you've already seen what they are, the most convenient way to find them is to say, okay, actually, if you have n particles with null momenta ki, define a one form, p mu, on your marked Riemann sphere by p mu is ki over sigma minus sigma I d sigma. And then what you can see is that geometrically, these equations just encode that p square is 0 everywhere. In fact, that tells you nicely already that there's only n minus 3 independent ones of them, or the other ones are related by Möbius. Yeah. Now you can nicely restructure them in a polynomial form and find that these have n minus 3 factorial solutions. So these are, what I want to tell you basically is that these are very well studied equations. Now, why are they so crucial? That is basically due to the factorization properties. So the nice feature that they have is that they relate the boundary of your moduli space, so really where your Riemann surface squeezes off and develops a bubble, to a factorization channel of the amplitude. And that is actually really easy to see, just encoded by having some points come close together, and then you can just see by just some algebraic manipulation that the sum over these scattering equations for the ones that come together is proportional to ki square, but these scattering equations are also very small, of order epsilon. So with basically just some power counting, this tells you immediately that your amplitude will develop the correct pole with the correct power. Okay, just to remind you, this basically tells you that any amplitude of massless field theories can be written in this form, because it just encodes the pole structure in a very convenient way for you. So in particular, this localization on the scattering equations is something very universal, and the only thing that defines what theory you're talking about is this specific integrand. Okay, now this is basically an integral over the moduli space of Riemann surfaces with marked points. That is so suggestive of some underlying CFT correlator on a Riemann sphere that you'd actually be surprised if you couldn't write something down. Maybe it has anomalies or something, but you should be able to write something down. And in fact, there is something very nice and very simple in a very natural gas, which is just a holomorphic complexification of the world line action for a spinning particle. So you see that you have a p dot d bar x plus psi dot d bar psi plus two terms, p squared and p dot psi. These will be two constraints imposed by two Lagrange multiplier fields. So the first thing that I want you to note is that all of these are, this looks very much like a string, but all of these are holomorphic. In fact, you can just simply check, I have spelled it out explicitly here that all of these are completely holomorphic, and that will be what makes the key difference. And we don't have any XX OPEs. The only OPEs are between P and X here. Now, the gauge fields E and chi here, they impose the constraints P squared and P dot psi, and that is really what tells you that this is describing a massless field theory, because it maps you onto the Ambitwistor space, the space of complex noun geodesics. And beautifully, the gauge fields, as you would expect them, impose both a quotient as well as the full quotient by the corresponding Hamiltonian vector fields as well. Now, this is, I've written down for simplicity a partially gauge-fixed version, but you can see that it has some additional gauge freedom that corresponds to shifting x by p and the corresponding supersymmetric version of that. So if we go ahead and quantize this, we end up with a completely free theory in the usual BRST quantization. I've written down, so we've gauged worldsheet gravity, and our these two come down here. And what we see is that just an analogy to string theory, in fact, the counting works exactly the same. We only get q squared equals 0 in 10 dimensions. So this theory is only critical, just the string theory in 10 dimensions. Something that I do want to mention is I'm discussing the RNS version that goes back to the original paper. There is this pure spinor version as well that's due to Nathan Berkowitz. Now, the vertex operators are, again, just in the, as usual, in the cohomology of our operator, BRST operator Q here. And what you can see nicely is that this enforces k squared and epsilon dot k to be 0. And this really tells you that your spectrum is in one-to-one correspondence with your spectrum of type 2 supergravity, if you go through it and check it. Okay, now I just want you to take a quick peek. I will keep the vertex operators here to just give you a brief flavor of how the amplitudes come out of this. What we can do is you can see that these operators don't depend on x at all except for the exponential. And in fact, descent won't change any of that because we only have px OPs. So what we can do is do the nice trick and take these into our free action and integrate out px. And what we find is that p is now defined by d bar p is 2 pi I ki delta bar sigma minus sigma I. And this should be something that immediately rings a bell because we can solve this and find p mu is ki over sigma minus sigma I d sigma, which is just the p that I gave you just a few minutes ago in the construction of the scattering equations. And in fact, you can see very explicitly if you integrate out after gauge fixing the moduli of this gauge field E, you end up with insertions that enforce the scattering equations, just delta functions in your amplitude. And so, just as a quick rundown, this really tells you why the correlator gives you these CHY amplitudes. In this case, I've written it out, as I've hinted at before, for supergravity, where each fermion gives you one of the Pfaffians. Okay, so as promised, now that I've given you a 10-minute rundown of what happens at tree level, let's move on to loop level. So, from what I've told you already, what you can expect is that we can play the same game as in string theory. So we expand in the genus of the worldsheet. We will do that in a minute, but what you'll see is that it has the same difficulties as string theory in doing explicit calculations with it. It doesn't really manifest the simplicity that you actually expect for the integrands in quantum field theories. And what you can actually do, though, is because this is localized completely on the scattering equations, just the moduli integrals, that you can use this localization to reduce this to the non-separating boundary divisors. So, in other words, you can collapse the A cycles and end up with just a theory that is, or okay, with just a formula that lives on the nodal Riemann spheres. We'd love to have the theory for it, but at this point, the formula. Okay, but to tell you why this is actually something that we would love to do, let me briefly tell you what happens actually at genus 1 for the world lead. Now, everything that I've told you about the calculation for the amplitude goes through as before, basically. We can still play the same trick, take the exponentials in the action, but now when we solve this equation, d bar p equals 2 pi I k I delta bar here, we have to live with the fact that first of all, we have a zero mode, and in order to parameterize this nicely, we want to basically put a delta p mu minus integral over some a cycle. So we've explicitly picked the basis of a cycles to make this assignment of the zero mode here. And then we have a bunch of terms that are just our usual theta functions. Now, the scattering equations, even without going through the full calculations, I've told you that the geometric meaning is really that they enforce p square equals 0. So just from that, you can already see we're setting, again, the residues of p squared to 0. This gives us something that very much looks like tree level, except for that we have all these theta functions floating around now. And p square of z0 is 0. Now, there's a very nice work due to Adamo, Casali, and Skinner that told us that what the full structure of the one-loop amplitude looks like. And you can really see this. You have the sum over spin structure, you have the GSO projection. This is something that should look very familiar from any string theory that you've seen. Except for, again, this localization on the scattering equations that completely fixes your moduli integral, but you're still left with a d10L up front here. Now, two remarkable things that I really want to point out. This is modular invariant if you don't fix an integration cycle for your L. Any real integration cycle will break this, but as long as you're happy with a formal argument, this is modular invariant. Okay, and there's been extensive checks on this. There's been factorization checks, and we know it has the correct tensor structure, but it's not immediately clear why this gives the nice rational integrands that we expect for quantum field theories. So what you can do, relying on the fact that I've told you that this is modular invariant, is you can use a contour integral argument in the fundamental domain. So going back, you can see that these fix all the marked points Zi. So the last equation, whatever your last equation is, I've chosen the p square right now, fixes the modulus tau. So on the support of the other equation, you're just instructed to sum over a bunch of solutions for this tau. And instead of summing over the solution, you can just swap the contour around and get the contribution around the boundary. Now the sides cancel out by modular invariance, the bottom cancels out, and we're just localizing on the tip here. So we're just localizing to tau equals I infinity, which, as I've promised you before, this is just the point where the torus actually degenerates into a nodal Riemann sphere. Now, if you're actually happier with a slightly different argument, you can see this very explicitly by just rewriting by the definition of this delta bar. This is just a del bar 1 over p squared up to a factor of 1 over 2 pi I. Now you can just use an integration by parts. Strip this off from here, land on the dq of the q, where I've defined my tau, my q to be e to the 2i pi tau. And now you can evaluate this trivially. Q equals 0 just directly corresponds to your tau equals I infinity. And what you can nicely see now is that you end up with a d10 L over L square. You're still completely localized, and you now just evaluate everything else at Q equals 0. So let me just stress this. You've reduced something that was quite complicated, something that had a bunch of Jacobi theta functions, to something that just looks as though it has 2 more points, but still lives on the Riemann sphere. Now you can make this very explicit. Just take the limit with a slight change of variables, and you can see that the P now really looks as though it has 2 more momenta that are back-to-back with the loop momenta L and minus L. And the scattering equations are defined in complete analogy, except for convenience, we've defined a quantity S here, where we've just subtracted off the double pole, just for convenience. Now, again, the integrand is completely well defined. We just have to take the Q going to 0 limit of what we know we got in the type 2 supergravity before. And the nice thing is that this is now manifestly rational. The other thing that I want to stress is that I've written this before with a D10L. Now, all the derivation that I've done is only valid in 10 dimensions. However, these final results, well, on the torus, they had to be 10-dimensional, otherwise they were not well defined. But these final results, these formulas, are valid in arbitrary dimensions on the nose. Okay, just as a brief point, I hope I have the time for this, I want to point out a puzzle that is something that is very characteristic of these formulas, is you can see that it only has an L square term here, 1 over L square, and in the scattering equations here, there's only linear dependencies on L. So naively, this seems to have the wrong power counting in L. Now, it is actually correct, but you have to put a little bit more work in, because the solution is that you actually have something that you could naively call just shifted integrands, which just means if you have 1 over some product of some propagators, you can write it as the sum of 1 over the propagator minus times the difference between 2 propagators. And you'll see that this has exactly the structure that you have here, up to maybe a shift in L. Now, this is nicely formalized by Q-cuts. Let me not get into it. Let me just tell you that this basically gives you the systematics for how to do this for higher loop order with arbitrary numerators and so on. Instead of doing that, I just want to give you a very brief example. So you can see that just for a bubble, you would have 1 over L square, L plus K square. You expand this out according to this formula. You shift the second term here to L goes to L minus K. And what you left is just 1 over L square times 1 over 2L dot K plus K square plus 1 over minus 2L dot K plus K square. So the other thing that this already tells you is that bubbles are automatically 0. These are automatically normalized if they're on shell. Okay, don't be intimidated. You actually don't have to absorb anything of this, except for we can do everything here for supergravity, and by applying the double copy that JJ told you about this morning, we can actually get super Young-Mills theory as well. I've defined the building blocks down here for you, but don't worry about the details. Essentially, this Park-Taylor factor just runs once through the whole loop. And using just usual string theory methods, we can actually do the same for non-supersymmetric theory. So we can write down both Young-Mills theory and gravity by just identifying the contribution from the NS sector. And in addition, for pure gravity, we do have to subtract off the number of B field and dilaton contributions as well. All of these, I should mention, all of these things are checked both numerical and by just doing the factorization limits. So we've checked that they factorize correctly and match all the Q-cuts. It's important that in this case they match the Q-cuts. Unitarity cuts are a bit too trivial in this case. They trivially give you the correct answer there. Now, something that I want to tell you, which is very recent work, which ties in nicely with the talk that JJ gave you this morning, is how to actually manifest this color kinematics duality. So I've pointed it out to you, but this is very much always at the integrand level before you do the moduli integral. So if you wanted to know how does this connect to the usual color kinematics duality that we know after we've done the moduli integral, I want to give you just a one-slide answer. So at tree level, this is very well established due to some recent work. And there's been a very beautiful paper for supersymmetric theories at loop level as well. But it's not clear how to do this for non-supersymmetric theories. However, if you look back at this slide, there's really no reason why this shouldn't work basically exactly the same way. And instead of going through a very detailed argument, let me just give you a very brief algorithm that tells you this is exactly what you need to do. So if you want to write down the BCJ numerator with manifest BCJ numerator at one loop, do the following. Just pick an ordered gauge. In some cases, it will be convenient to sum over these. And then just split all your particles into two groups. I've called them row 1 and row 2. And find all what are called ordered splittings of rho 2. Think of these just as this tells you how the color ordered amplitude that you're looking at differs from the ordered gauge that you've chosen. And then just calculate this quantity here. This is the numerator, where these W's are just some traces of your external particles. The W's are defined, the W tildes back here are defined as epsilon dot F's, and the Z's are just the external momenta that come before, external and loop momenta that come before both in the ordered gauge and in your color ordering. So this is an algorithm that's very brief that you can put onto a computer and that would spit you out everything to arbitrary multiplicity. So this really works to any order of external particles. Now, without going into detail, the proof basically relies on expanding the Pfaffian that we had into Park-Taylor factors and using the scattering equations in an intelligent way. Now, before I run out of time, I just want to give you a 1-minute answer to something that you should have been worried about since I told you about this. What happens after one loop? Because really, at one loop, this could be just a restatement of the Feynman-Tree theorem. So beyond one loop is really the point where you see whether this is just some arbitrary feature that you can make work, or whether this is something that is truly a statement of the theory. So just to remind you very quickly how this is done, we start on a Riemann surface. We use residue theorems to contract all of our cycles, so we end up on a nodal Riemann sphere. And just as a quick sanity check, we started out with 3G minus 3 moduli. The residue theorem reduces us to 2G minus 3 moduli. This is exactly the number of points, the number of moduli for the new points that we actually need. Now we can write down the one form directly, and since I'm out of time, let me just state it for you. It does work at 2 loops. So it works at 2 loops for n equals 4 super Young-Mills and for type 2 supergravity, both planar and non-planar. So this is something that genuinely generalizes beyond one loop. And since I'm done, let me just put this out there. I'll skip the summary. I'll just say there's a lot to do still, both at 1 loop and at 2 loop. At 2 loop, we only have results at 4 points. It would be very nice to generalize these, especially in light of the fact that at 1 loop and at tree level, there's really no difference. It's just simple to write down all multiplicity results. Medium term, it would be beautiful to extend this to actually a model on nodal Riemann spheres, because this is really what you would need to do to push this to higher loops, I believe. And long term, what I've told you is something that is remarkably reminiscent of string theory, but the actual connection with string theory is not manifest in anything of what I've told you. It would be beautiful to see the alpha prime going to 0 limit and landing on these theories directly in an explicit way. Thank you.
Thank you very much for this very nice talk. Questions?
So when you discussed the loop integration, you first fixed all the moduli and then you left till the end the integration over the loop variable. Is it possible to integrate first the loop variable and then get some other representation?
I would love to do that. So what you'd expect is to end on some sort of Stringer parameterization with that. What I'm not quite sure about how it would work is how you would pick the integration cycles afterwards. So it's been something that's been floating around as an idea in the community for a very long time, but I don't know of anyone who's actually managed to tie it down and make it work directly.
So you mentioned that some of your results make sense for arbitrary dimensions. So what do they mean in arbitrary dimensions? And in particular, what are the results that you get? Do they have any interpretation in arbitrary dimensions, and in particular for d bigger than 10?
So arbitrary dimensions, obviously there's some restriction on sort of especially supersymmetric ones. In dimensions lower than 10, they just give you the actual field theory results. So for example, you could just write this and just plug in your 4D momenta and 4 depolarizations, and you would just land on the result without having to do anything else.
This is probably a stupid question, but do your results have any implications for finiteness of supergravity?
So I've maybe not stressed this enough. So these only make statements at this point for the integrand. And at this point, we're well below anything that JJ and Svi and so on can tell you. So at this point, there is no prediction yet. The hope would be, especially with what I've been telling you with this algorithm, combined with sort of what we know about how the model, what the model on an Euler-Riemann sphere, what we expect it to look like, and what we know how it works at one loop. If the model works as we expect it to work at higher loop order, then this algorithm would generalize. So potentially, this algorithm would give you a way to immediately land on the BCJ numerators, and then it would help in making a prediction. But at this point, there's no prediction yet.
I don't see any further questions, and in view of time, let's thank Yvonne and all the speakers of this session.